All right, for our lesson in geometry on Monday, I think Monday's the 27th of March. I wasn't planning on being gone, but I'm going to be helping Ms. Schroll score the test from Test Fest. So section 10.3 is all about using chords of circles. And if you do not have your book, once you start working on your homework, you might want to have your book in front of you for more examples. It starts on page 546. The definition of a chord is a segment with endpoints on the circle. Segment with endpoints on the circle. Or on a circle. And then with segment, just don't forget, and maybe even take your pencil or your pen and you put a line across to show that, yep, it's a segment. Petty chord. Nope. Sorry about that. An arc is a portion of the circumference of the circle, or the outside of a circle. And then last but not least, a diameter is a segment that divides a circle into two semicircles. Divides a circle into two semicircles. Now, in this section, we're going to get a lot more in terms of relationships about chords and how we can find values. We'll be using a lot of algebra. When we talk about dividing into two semicircles, just a reminder that in a circle, we go all the way around 360 degrees. That semicircle idea takes us to the 180. Half of it is 180 around. Semicircles are both 180. With arcs, we have major and minor. If you were absent on Friday from class, you will be on Tuesday when you see me making up your 10-1, 10-2 quiz. Moving into the theorems that we'll use. Theorem 10.6, congruent corresponding chords theorem. If you have two chords that are congruent, what it's telling us is that the minor arcs are going to be the same. If you know two chords are the same length, then the arcs on the outside or the circumference of the circle are also going to be the same length. We'll see this in use on our extra practice and examples. And again, in your book, this section starts on 546. There's plenty of examples to follow besides what we have in this packet. If the diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So that means that this diameter is hitting this chord. That's going to make the segment F to H congruent to H to D. And then these two arcs here, F to G and G to D, would also be congruent. Now, when we go to perpendicular chord bisect or converse, if you know that we have congruent arcs, then you can conclude that this must have been a diameter. If you're not sure if it goes through the center, if it is bisected, if you're not sure if it goes through the center or if it's a diameter, if it is bisected a chord that you can tell is clearly not going through the center, then that must be the diameter. Equidistant chord theorem. You've got congruent chords if and only if they are perpendicular to segments coming off the center that are the same length. So the one thing in here on the 10.9 theorem is I would just have those markings there, that those two have to be the same length. And if that's the case, then we know that these chords A, B, and C, D are congruent. Let's see this in use in our extra practice. For problem number 1, let's take a look at what we have here. So we've seen a lot of, I'm just grabbing a calculator, we've seen a lot of circles that gave us a ton of angle measures. When I'm looking here, the only angle measure that I see is right here at the 42 degrees. And one thing that I do know, and I'm going to come over on this side, and I know that that angle is going to be 45 degrees because they're vertical angles. Remember, oh, 42, sorry. Too many things at once here. So if this angle is 42, this angle is also 42 because they're vertical. Now the other thing that I think I'm going to do before I start working these problems is figure out what's left in terms of an angle measure that's going on these vertical angles at Q. If I go and take my 360 minus the 42 minus the 42, that leaves me with 276 degrees to split between these two. If I divide 276 by 2, I know that this at Q I'm dealing with 138 and 138 because all the way around had to be 360. Let's see if that helps us find anything. Find the measure of arc WX. Well, arc WX would be here, and that's coming off of this 42 degree angle. The measure of that arc would be congruent to 42 degrees, the central angle that it's opening up. How long is segment Y to Z? Well, then let's look at these measures that are here. If these two angles are 42 degrees and W to X is 3.6, I would expect that this also from Z to Y would be 3.6 as well. Now this isn't an angle measure, it's how long that segment is. W to Z, same kind of thing. If I'm over here on XY at 9.2, my WZ is also going to be 9.2. Measures of these segments, not an angle. And then last but not least, the measure of, I just dropped my calculator, the measure of arc X to Y. Good thing we did that central angle before. That's going to be that 138 degrees that we found when we figured out what was left out of 360 for the angles at Q. So that would be 138. Now when we go into the next problems, we're dealing with these relationships for the new theorems that we had talked about on the previous page. And in number 5, what I see here is I have a diameter that's perpendicular to a chord, and the theorem, I think it was diameter perpendicular to a chord. Then the first chord is the diameter, we got it. The diameter of a circle is perpendicular to chord, then the diameter bisects its chord. So that means that I can set these two equal to each other. So 2x minus 4.1 is equal to x minus 0.5. First thing I'm going to do is subtract 1x from both sides. That's x minus 4.1 equals, and this is going to be negative 0.5. Don't forget to take that negative sign with you. After you've subtracted out x, it's negative a half that's left. And then I'm going to add 4.1 to both sides of the equation to find out what x is. And negative 5.5 plus 4.1 is going to give us 3.6. So x is equal to 3.6 here. Same relationship going on in number 6. Let's set 2x plus 1 equal to 3x minus 5. Solve this equation many ways, but I'm going to start it by taking away 2 x's from both sides. 1 is equal to x minus 5. 3x is minus 2x is going to give me 1x. I'm going to add 5 to both sides. X is equal to 6 for problem number 6. And again, this is based on the theorem, which one was it? Theorem 10.7 from the previous page, that I could set those chords equal to each other. Theorem 10.7. This would follow along with example 2 in your book from page 547. Example 2, page 547. Now, in number 7 and 8, we're dealing with a little bit more of a complicated drawing. What I'm gathering is that they want us to use the idea that this chord AC is the 5x minus 2, and it would be then congruent to this chord ED, that's the 3x plus 2. So to get this started, they want me to find the radius of the circle. That's going to take another step, but to get this started, I really need to find out how long these chords are. I'm going to do that by setting these chords equal to each other. 5x minus 2 equals 3x plus 2. If I take 3x's away from both sides, 2x minus 2 equals 2. I'm going to add 2 to both sides of the equation. 2x equals 4. I'm going to divide both sides by 2, find out that x is equal to 2. Now, I've got to go use that, because what I need to do is actually figure out what the radius of this triangle is, and that's going to be a little bit of a trick because I don't see a radius marked. But what I want to show you is that a radius is going to be like from P to D. So I'm going to focus right now on this right triangle that I just shaded in here, because the radius is going to be, I'm going to put an R right here from P to D. That is the length of the radius. And then what else I know is that this leg of this right triangle, and that R is representing a hypotenuse. Let me bring that little triangle over here. R. This is from P to E. There's P, there's D, there's E. From P to E is 3, and again I've got R here on my hypotenuse as the radius. Now I can figure out what E to D is, and the way that I'm going to figure out what E to D is to be able to use this as a right triangle, I'm going for the Pythagorean theorem. The way I'm going to figure that out is I'm going to go plug in X is 2, 3 times 2 is 6, 6 plus 2 is 8, D to F is 8. These guys are going to be congruent to each other, so E to D must be 4. Now, what I'm recognizing about this one is that, and I could have done this work on a right triangle created above this too. I'm creating the right triangle just kind of where visually my eyes went. I'm going to use the Pythagorean theorem. R squared is equal to 3 squared plus 4 squared. And I'm actually recognizing this as the smallest Pythagorean triple. R squared is equal to 9 plus 16. That makes R squared equal to 25. When I take the square root of both sides, then R is equal to 5. So the work that I had to do involved finding X and then using that to find measures that help me make that right triangle. Now example 4 in your book on page 548, example 4 on page 548 also has the same process and setup and that many steps to go through. We're going to take the same idea to figure out what X is on number 8, and then I'm going to go find the radius like we have to. Now, this is set up a little bit different, a hair different. We know these chords are the same length, and that tells me then that these segments O to Y and O to Z are the same length. So 4x minus 5 equals x plus 4. If I take x away from both sides, 3x minus 5 equals 4. If I add 5 to both sides, 3x equals 9. Finish by dividing by 3 on both sides. X is equal to 3. Now let me go and shade a triangle. I'm going to shade the right triangle O, W, Z. And let me bring that over here for us. O, W, Z. My right angle sits there. The radius needs to be found. Now, what I've got in this case is O to Z was expressed as x plus 4. Well, I've got x equal to 3. 3 plus 4 is going to make O to Z 7 units long. Now, the other thing that I can go with here is that if the entire W to X is 20, that means that at Z it's been split into 2 parts that are 10 each. So my right triangle now has legs that are 7 and 10, and my radius is the hypotenuse of this right triangle. Now, R squared is going to be 49 plus 100 is 149. So the radius of this is the square root of 149, and I'm in my calculator, and I'm estimating that to be about 12.2. So finding my X, going to look and bring off that triangle, and using that triangle to help me solve for the radius. It was a multi-step problem that involved some good algebra solving and our Pythagorean theorem. You have problems to work on. Practice 10.3 will be put in front of you. I expect you to attempt everything and have it ready to discuss when I see you at the start of class on Tuesday. Good luck.